Each set of parametric equations below describes the motion of a particle in two-dimensional space. For each particle, we'll create a motion map. Then we'll use calculus to find the velocity and acceleration functions. Let's draw and label a few relevant position, velocity, and acceleration vectors. Now we have the position of the particle in parametric form, which just means that it's separated into two equations, one for x and one for y. We're going to want to combine that now into one vector form formula that'll give us the position using I hat and j hat. So the formula for this is just to take your x function and attach that with I, and then take your y function and attach j to it. So it's going to be real easy here. We'll just say that r of t is equal to t times I hat minus 4 times j hat. All right, next we'd like to plot a couple locations where this particle will be. So for that, we could make a table if we like. I think I'll do that down here. We'll have t, x, and y as our columns. Now we could pick, let's say, a time of -4, -2, 0, 2, and 4. We can pick anything we like. Then we just want to plug it into the formulas. So our x is going to start off being -4. And x is always t, so whatever the time is, that's going to be our x location. When it comes to the y, though, we see that it's a constant -4 no matter what the time is. It doesn't depend on time. So we'll have this, and now these are going to be two-dimensional coordinates that we can plot. So we want -4, comma -4. Let's see. That's this location. We've got -2, -4. We've got 0, -4. 2, -4. And 4, -4. As we can see, as time goes on, our particle is moving to the right. We can create arrows which represent the position vectors. These point from the origin to where our particle is located. All right, now we want to take the first derivative so that we can also sketch the velocity vectors. We want to take the derivative of the x function and the y function just separately. So the derivative of t will be 1, and the derivative of a constant -4 will just be 0. And so we get this formula, v of t is simply going to be I hat. Now, what is the interpretation of this and how do we draw it? Well, we want to attach arrows to our blue dots here, representing which direction they're going, and the length represents how fast they're going. So our arrows should be pointing in the positive I direction, and they should have a length of 1. And as we can see, the velocity is constant for this particle. It's just moving across the page to the right, and is neither speeding up nor slowing down. Now we can take this even farther and find the derivative of the velocity function, which would be the acceleration of the particle. Now we can see that the particle is moving with constant velocity, so we should already conceptually know that there is no acceleration to this particle. But the calculus will reveal that as well, because if we take the derivative of 1, which is a constant, we're just going to get 0. And of course, the derivative of 0 is also 0. And so for our acceleration, we get something called the zero vector, which just means there's no acceleration. Go ahead and try the next one if you like, and then I will put my answer up in a moment. Okay, for our position function, we will have t I hat plus negative t plus 3j hat. It's all about just taking these parametric equations here and then just plugging them in, attaching them to the correct unit vector. X goes with I, of course, and Y goes with J. Now let's make a table for this so that we can plot our particle. I'm going to start this one off with a t of 0, and then we'll do 1, 2, 3, and 4. Alright, so if t is 0, then x is 0. If t is 1, x is 1. If t is 2, x is 2, and so on. However, when it comes to our formula for y, if we plug in a 0 for t, we'll get 3. If we plug in a 1, we'll get 2. If we plug in a 2, we would get 1. And then we'll get 0, and looks like negative 1. All right, let's plot these coordinates. We're going to have 0, 3, which is this point here. We're going to have 1, 2. We'll have 2, 1. And we can start to see what this particle is doing. All right. If we draw our position vectors, we'll get this. And it keeps going, of course. Now we'd like to draw the velocity vectors too. So let's take the time derivative of the position. So we'll get 1i. Let's see, take the derivative of negative t plus 3. We'll actually get negative 1j. All right, so what's that going to look like then? We need a horizontal component of 1 and a vertical component of negative 1. And so what our object is doing is it's moving down and to the right. Okay, the black represents our velocity. The red represents our positions. Now when it comes to the acceleration, as we can tell, this is going to be a constant velocity object, and we're going to have, yet again, a 0 acceleration. This next one's a little bit more complicated. We've got a t squared involved. So let's see if this gives us more interesting derivatives. We'll have ti plus negative 1/4 t squared plus 4 times j. That's our position. And we'll go ahead and make a table. I'll try a t of 0, 1, 2, 3, and 4. All right, if I plug in 0 here, I get 4, so that's going to start us off right here. If I plug in a t of 1, I'll get 3.75. Let's plug in a t of 2. We'll get 3. A t of 3 will give us 1.75. And finally, when t is 4, our y will be 0. The motion of this particle mimics an object that's in free fall near Earth's surface. There's obviously some kind of acceleration happening, so let's reveal that through the differentiation. Now for our velocity, let's see, we're going to get 1I. Over here we'll get negative 1/2 t times j. That's going to be our first derivative there. All right, so let's extend our table. We want to now make an additional column for the velocity. And I can keep it in vector form if I want. So when t is 0, we're going to get 1I, and there won't be a j component, because if you plug in a 0 there, it'll eliminate the j component. Here, when t is 1, we're going to get I minus 1/2 j. If t were to be 2, we would get I minus j. If t is 3, we'll get I minus 3/2 j, and so on. We want to plot those velocity vectors. So the first velocity vector points directly to the right. That's what the I hat tells us. But then we see that the velocity direction starts to change. Now it's going to go to the right and down a little bit. Next, we're going to go to the right and down equally. Here, let's go to the right, but we'll also go down substantially. And one more. We can see how the velocity of this particle is changing with time. Something's causing it to be pulled in the downward direction. But we notice that the horizontal component isn't changing at all. So what's causing it to bend like that? Well, there must be an acceleration. So let's go ahead and find the derivative of the velocity. We'll get 0I minus 1/2 j. Or in other words, it simplifies to just negative 1/2 j. All right, what I'd like to do next is let's draw the components Vx and Vy. Now, Vx is, of course, the first component here, and Vy is going to be the vertical component. Now, the horizontal component, it doesn't change. It's just always to the right. But the vertical component is changing. It's getting larger and larger in the negative direction. There's our components, Vx and Vy. One more motion map that would be really useful here would be one showing the acceleration vectors. So I'm just going to draw the blue dots one more time. Okay. The acceleration is all in the negative direction, and it's always constant. So if we draw it, it has to be attached to the dot that it's affecting here. And we just want it to always be pointed down and always have the same strength. Now later in these videos we'll see that acceleration is caused by a force of gravity if we're talking about a free fall situation near Earth's surface. And the pull of gravity is always going to be constant, so that will be the type of acceleration we see for a projectile that's in free fall.